Okay, let's review this really quickly. Remember, when you are finding your inverse, your rule is to switch x and y to solve for y. And so remember, in function notation, this represents your y. So when we switch those, we're going to say x equals to y minus 4. To solve for y, we add the 4 and divide by the 2. And so remember, divide each piece by 2. 1/2 x plus 2 equals y. And our final step is to replace that with our function notation. They wrote it over 2 like this, but I would actually write it g to the negative 1. That's my inverse notation, 1/2 x plus 2. You'll notice we also talked about domain. Domain is here all real numbers. It just means that there are no limitations on my x value that I can use. For the second one, again, this represents my y, so x equals negative y squared plus 1. I am going to subtract that 1, divide each piece by the negative 1. So y squared equals negative x plus 1, or I think they wrote it 1 minus x. And then to get rid of my y, I'm going to take the square root of both sides. So y equals the positive and negative root of 1 minus x. There are limitations on this one. Inside my root must be positive, which is greater than or equal to 0. So I do need to set a limitation that tells me that. When you do that, just solve for your x. Subtract your 1 over, divide both sides by negative 1. Remember, when we divide inequality, we flip that when we divide by a negative. So x has to be less than or equal to 1. And so you'll notice when they wrote this, the first thing we have is our inverse. They used inverse notation, positive and negative square root of 1 minus x squared, which is what we have here. And then they define the domain saying it can be any x as long as x is less than negative 1. And this just tells me it's real numbers. And so that's my notation there, that x must be less than or equal to 1. That is my domain. All right, let's talk about exponential equations. Exponential equations are defined by an equation where my exponent is the variable. We have dealt with equations that have exponents. For example, y equals ax squared plus bx plus c. This is a parabola. We do have an exponent here, but the difference between that and an exponential equation is that in an exponential equation, my exponent itself is the variable. Now you'll notice there's some stipulations. B has to be greater than 1 and specifically cannot be greater than 0 and cannot be 1. And so B cannot be negative and it cannot be equal to 1. If you think about it, if you were taking 1 to any power, it's just going to be 1. And so it's not going to be growing exponentially. In fact, it's going to be staying exactly the same. But this will be the format for the exponential equations, and you may have it being multiplied by something, so very often it's going to look like some number times that base to a power. And so if we look at what the graphs look like, you'll notice that for the graphs that have a number greater than 1, they are growing. So the y equals 3 to the x, y equals 2 to the x, those are getting larger. And then if you look at the ones that have fractions in there, you will notice that the fractions, 1/3 to the x, is getting smaller as you go to the right. And so if it is a fractional base here less than 1, you're going to see them continually getting smaller. A number greater than 1, they're going to be continually getting larger. And so this is what the graphs are telling us. Any number can represent the base that is greater than 1, and it is going to be increasing. Remember, your range then is always positive. We're not going to have a negative range here. And if it is a number between 0 and 1, that graph is going to be getting smaller. So one of the most famous of the growth functions is the account balance, where you're doing compound interest. And I do write this a little bit differently. So instead of calculating my R, I am going to go ahead and put it into this format. So we're going to say that our account balance, which is what we're looking for, is going to be our principal. This is the initial amount. Principal amount represents your starting amount that you invested. Starting amount. And then we're going to say 1 plus, and this is going to be your rate divided by the number of times it compounds. And by that I mean, if it compounds quarterly, that's going to be 4 times a year. If it compounds daily, that's 365 times a year. So this N represents the number of times per year that it compounds. And then your R represents your interest rate or your rate of growth. All right, and then you're going to raise everything. The exponent here is going to be that same N, the number of times that it compounds, times the number of years. So T here represents the number of years. And so if you look at this word problem, we are investing $10,000. So if we look at my equation here, my $10,000 represents my principal, how much I initially invested. We are earning 3%. So that is my interest rate. You're always going to write it in decimals, so 0.03. Compounded daily, so the number of times it compounds is going to be 365 times in a year. And we are going to raise that to the 365 times however number of years. And so that is my just function modeling that they're asking for. The second piece is saying after 25 years. And so if I want to find out exactly what I'm going to make in 25 years based on this model, I'm going to plug all of that in, including the number of years, which is 25. So in your calculator, you should be able to put all of that in. You're going to say 10,000. You're going to multiply that by 1 plus. Make sure you put parentheses when you start this addition piece. But inside, it should do order of operations. You are going to do your exponent little button. And then here, sometimes you do need to open parentheses if it doesn't automatically do that for you in your calculator. And when you put that all in, remember dollars and cents, we're going to round to 2 decimal places always. You should get $21,169.35. So go ahead and try these two. The first one just wants you to set it up, and the second one wants you to actually work it out. So we talked about exponential functions, we talked about using them for compound growth, and now we're going to talk about using them to look at other things and what all it can tell us. So the first thing I want to point out is that we have a form for exponential equations, which we did a little bit in the last section, but your form will always be y equals. In the other one we had initial investment, but your A is going to represent your initial amount. Your b, again, is your growth, and it's being raised to an x value where your exponent is. And so this one wants us to solve for the general function here. We've done something like this with linear equations. For linear equations, we would use these 2 points to find our slope, and then we would use that to find our y equals mx plus b. But now we're going to be plugging these two x's and y's into our exponential equation. So we're going to write 2 different equations using these 2 different points, plugging in my x and my y. So I'm going to say y, which is 12, equals a times b to the x, which is 2. And then I'm going to do the same exact thing for my second point. I'm going to say 96 equals a times b to the x, which is 5. Now, just like any time I have multiple equations with multiple variables, the first thing I want to do is see if I can maybe solve for one of the variables, get it by itself, so I can use substitution. And if you look, this a is going to be the easiest thing to get by itself. On this left equation, I will divide both sides by the b squared. That equals a. And on this right side, I'll divide both sides by the b to the 5th, which will also give me a. And anytime 2 things equal the same variable, I can just set them equal to each other. So I can say 12 over b squared equals 96 over b to the 5th because they both equal a. Now I can have something I can solve. I will say, when I'm trying to move one variable or the other, I always choose to move the higher exponent when it's in the denominator. So I'm going to multiply both sides by b to the 5th. Over on this right side, they cancel. So when you're looking at functions that are in an exponential growth or decay, we've already learned that it is written y equals a times b to the x. And this b represents really your growth factor. Your rate of growth or decay then is going to be found using this formula, just like we did when we did compound interest. So if you have your B, you can find your rate by just subtracting that 1 over. And then you can tell if it is exponential growth or decay just by looking at the B. If your B is a larger number than 1, then you should have added a positive R. Or if it is a number smaller than 1, you should have subtracted the R. And so by just looking at these equations, you can tell what your initial amount is, what your growth factor is, and what your rate of change is. So in this case, A, your initial amount is going to be that 10. Your rate of change is going to be 0.5, but then you want to make it a percentage, so multiply by 100, so 50%. And then your growth factor is going to be what happens when you add that 1 to your rate. So growth factor is going to be that 1.5. If you look at B, your initial amount is 45. Your rate is going to be negative 0.25 or negative 25%. And then your growth factor is going to be 0.75. For the ones that already give it to you, so like initial's easy, we have a 20,000 that's initial. But here they've given you your growth factor. So our growth factor is 1/2. To find my rate, this represents my B, so B minus 1 will equal my rate. So if I subtract 1 from that B, then I know my rate is negative 1/2 or negative 0.5. So my rate here is negative 0.5 or negative 50% if I wrote it in percentages. And then for this last one, what you want to keep in mind here is that the initial is a 1. You can think of it as 1 times 3 to the D. And so my initial is going to be 1. Again, they gave me my growth factor of 3. To get my rate of change, I'm going to do this growth factor minus 1 or 2. Which if you multiply by 100 to get percentage, that's 200%. All right, so when you have word problems then, you're going to read the word problem to figure out what your initial amount is, what your rate of change is, so that you can then get your growth factor. And so as we read through this problem, beginning with a population of 2 million, and they want us to do it in millions of people, they just told me my A, which is 2 million or 2. Nevada was the fastest growing state from 2000 to 2010 with an average annual increase of 3.2%. They just told me my rate. So this 3.2% is my R. They gave it to me in percentages, so I'm going to write it in decimals. So they just gave me that piece of it, which means I have my exponential function. And I can rewrite it to go ahead and add that 1 to the 0.032. But that's my growth function. It says use this function then to determine Nevada's 2010 population. Well, if I started in 2000, my X or my time would be how many years away I am from 2010. So I would just plug that in. I am 10 years away. I have been growing for 10 years, so I'm just going to plug that in. When I plug that into the calculator and round it, I will get approximately 2.7 million people is what it would be in 2010. Then it gives me another problem. It says determine the average annual percent increase in population during the 1990s if Nevada's 1990 population was 1.2 million. So now they actually want us to find the rate here. And they've given us basically a starting of 1.2, and then we would have the ending of 2 million. So for this last one, we are going to say that, well, we know it ended at 2 million in the year 2000. In 1990, it started at 1.2 million. We do not know what the base here is, but we know that it was 10 years that it happened. So we would do the division of 2 divided by 1.2 to get that b to the 10th by itself. And then we would, to solve, we would want to get that 10 out of the exponent. And remember, to solve these, to get the 10 out of the exponent, you can raise both sides to the reciprocal. The reciprocal of 10 is 1/10. So in your calculators, you could really do it to the 1/10, which would give you your b. So that would solve for b. b would equal 2 divided by 1.2 to the 1/10. And then to find your r, remember, you just subtract 1 from your b. So the rate here is 0.052 to get it in percentage, multiplied by 100, 5.2%. So example 4 is similar to example 3, except that now they're talking about a decay. And so they're telling us that the population fell from 60,000 in 1880 to 47,000 in 1890. So they want us to use a decay function to determine the percent decrease in population. So again, we have an ending amount, which is going to be the 47,000. We have our initial amount, which is 60,000. We do not know the base, but we do know the number of years, and it was from 1880 to 1890, so that we know it's 10 years. And so again, we would solve for this by dividing by that 60,000. So we get 47 over 60 is b to the 10th. And then again, to get that 10 out of the exponent, we raise both sides to the reciprocal, which means that b will equal 47 over 60 raised to the 1/10. That is going to be our b. And remember, to find your rate, b equals 1 plus r, we just subtract the 1. So b minus 1 equals r. So we get a negative 0.024, again, in percentage, negative 2.4%, which makes sense because it is decaying, it is going down. They're telling us in this next piece, if we assume it continues to decrease at the same rate, we can estimate the population in 1900. So we can do this 2 ways. If we start at 47,000, it's only 10 years from 1890 to 1900. Or if we start in 1880, we can use 20 years. It just depends on which one we start with. So if we use the starting of 60,000, then we will have 1 plus our rate of negative 0.024. And that will be from 1880 to 1900. It's 20 years. Or you could start with 47,000, which was the intro amount in 1890, and do the same rate of change, but only do it for 10 years. Either one of these is going to give the same answer when you plug it into your calculator, which is going to be about 37,000 if it continued to decrease. The last type of word problem that is pretty standard for exponential problems is your radioactive decay or half-life. And so when you think half-life, just the term half kind of indicates what your base is. Your base is always 1/2. You do have a starting amount. This is the amount of substance that you started with before it started decaying. Time always represents typically the number of years, because half-lives are given to you in how many years it takes typically for something to decay. But sometimes it'll be faster than that. And so just pay attention to how it gives you the half-life. It gives it to you in years, then your time will be also in years. And so you basically always use this occasion. Initial amount, your base is 1/2, and then the number of years divided by how many years they have given you for the half-life. So if you look at this problem, they tell us the half-life of carbon-14 is 5,730 years. A piece of wood believed to be 4,000 years old contains 19 grams of C14. Predict the original amount. So they have given us where it is now, which is the F of T. So we now have 19 grams. They're asking about the original amount, which again is my A, always my A. And then they have told me, we always know my base, and they have told me the time. 4,000 years old, that is the time. And then they've also given me the half-life, 5,730. And so if I were solving for A, I would divide by this whole group, 1/2 to the 4,000 divided by 5,730. And I would divide both sides by that. So in your calculator, if you're solving for your initial amount here, you would say 19 divided by, and then you would open parentheses and use your half-life, which is 0.5. Use your little exponent button, and then you do want to do an open parentheses here to do your division. Then close parentheses and close parentheses. And when you do all of that, you'll get that it initially had about 30.8 grams when it started. So that would be the first question here. Predict the original amount. The second question then wants us to predict then what it will be 100 years from now. So now, what we have right now is the 19. So when I'm doing this time I am solving then for what it will be. So we're going to start with what we have right now, which is 19. We are going to use the same base, which is 1/2. And then 100 years from now, we will just do 100 in the time, and we will keep the half-life as 5,730. And in your calculators here, if I'm solving for what it is now, you would say 19. You would do multiplication. You would do 0.5, and then you do need to force that division in your exponent. And when you do that, you will get that in 100 years, it'll be approximately 18.8 grams. So you can see half-life basically means for this one, whatever you start with, let's say you start with 20 grams, it will take 5,730 years for that 20 grams to become 10 grams, to be cut in half. And so you can see that it takes a long time for something with that long of a half-life to break down.